So as you can imagine, there is going to be momentum advection as well. So momentum itself is u times the density, and the currents are going to advect this momentum as well. So it's good that we can represent the shear in the wind stress directly to the shear in the water column itself, to see how the vertical eddy viscosity is going to penetrate the momentum into the ocean. Obviously, for the wind stress momentum penetration, vertical eddy viscosity is very important, because that's how most of it is getting put in, even though wind-driven currents are dragging the ocean and often in the direction of the winds near the equator, because F is small, the deviation F times U or V is small, and the winds are deflected, the currents are deflected more from the winds as you go away from the equator. So the horizontal eddy viscosity and the vertical eddy viscosity are very different in that sense. Plus, as the ocean moves, when the winds try to drag it, the friction between the ocean and the atmosphere are going to depend on how fast the ocean itself is moving, as opposed to land, where the land doesn't move, so the friction is higher on land, just as a point to make. Okay, so where does the viscosity itself come from? So if we write this equation as let's say the balance of viscosity with the friction and wind stress here. So the viscosity itself is related to the vertical shear, and says compared to the surface velocity, if you want to drag the water below, then how much stress do you need? That is kind of the definition of the viscosity itself. When you have motion, kinematic viscosity is basically a measure of how much stress you need to put to drag the fluid below with the fluid above, right? So that's the shear and that's the stress that's going in. So you can write tau x over rho then as the viscosity times du dz. Okay, so you can think of the definition we got for 1 over rho tau x del tau x del z as del z of nu du dz. So then 1 over rho del tau x del z, assuming nu is basically constant, we can write that as del squared u del z squared, and molecular viscosity is not going to be very efficient in penetrating the momentum, so we're going to write it instead as eddy viscosity, as we did before. So long story short, du dt equal to ah del squared h u plus 1 over rho del tau x del z, and del v del t equal to ah del squared v plus 1 over rho del tau del z. Now we can write actually the momentum advection equation just like we wrote the advection equation for salinity and temperature. So the acceleration then can be related to just how the currents themselves are advecting the momentum. So momentum advection term then looks very similar to what we had before. Du dt is minus v dot grad u, dv dt is minus v dot grad v, del w del t is minus v dot grad w, where v is of course the vector uv and each momentum is going to be, for example, u du dx minus v dv dy minus w du dz. So how the zonal momentum is being carried based on its gradient in the zonal, meridional and vertical direction by the zonal velocity, meridional velocity and vertical velocities. I hope it's becoming intuitive how to think about this. We had dt dt and ds dt written as u dt dx v dt dy w dt dz and so on. So here we are advecting momentum itself by the current. So these are obviously what are called non-linear terms, because the zonal momentum advection, it depends on the gradient of the momentum itself. Right? So you can look at the horizontal advection of meridional velocity. So in that case it's minus v dv dx minus v dv dy. So just note that it is dv dx dv dy because we are worried about horizontal advection of meridional velocity, and it can be advected by zonal velocity and meridional velocity. That's how we end up with these terms. During the last pentad of 2018, from 1/3 degree Oscar surface currents that we talked about before, derived from the sea surface height and winds, we will see later that sea surface heights give us geostrophic currents. Then we have to add what are called Ekman currents or wind-driven currents to get the total Oscar surface currents. So here the absolute value of minus u dv dx and minus v dv dy averaged over that year. Ratio of meridional advection of meridional velocity, so minus v dv dy to the total horizontal advection of meridional velocity. So this is minus v dv dy divided by this term, and in C we are looking at the absolute values, so it's the magnitude of minus v dv dy divided by the total. Okay, so just to tell you that the gradients of meridional velocity in the zonal and meridional directions tell you how the advection term, meridional horizontal advection of meridional velocity, looks like. So obviously u is coherent on large scales because the winds are trade winds and they create large scale south equatorial and north equatorial currents in the tropics, and there are zonal currents, coherent zonal currents here in the western boundary currents peeling off and becoming the North Pacific current here and the Gulf North Atlantic current here, and in the western boundary currents you will have strong meridional currents with short zonal currents and so on. So each one has a contribution dominated by u or dv dx and v or dv dy, and where they are coherent. So when you look at the total advection it looks quite noisy, but when you look at the magnitude you can see where the meridional where the horizontal advection of meridional velocity is strong, of course where the zonal currents are very coherent or meridional currents are very coherent, like here and here and in here, for example. And the magnitude or the ratio is strong where v dv dy term is strong. Again, shows up in where the divergence near the equator is strong. It is just a way to think about the magnitudes. So we'll come back and put together the equations of motion by combining the pressure gradient term, the wind stress term, and the momentum advection terms back into our Newton's law of motion, and that will give us the full nonlinear governing equations for momentum called the Navier-Stokes equations, which are nonlinear equations which cannot be solved analytically, so they have to be solved using computers, and this is why we end up with general circulation models, for the ocean and the atmosphere, often with some simplifications where you have just the wind-driven circulation model, or just the thermocline model, or the thermohaline circulation model, and so on and so forth, or tropical atmosphere model, which is a simplified linear shallow water equation model dominated by waves, and so on and so forth. But once we look at the full governing equations, we can talk about where the simplifications come from. And one of the simplifications we already talked about is, of course, the vertical momentum equation, which we had reduced to hydrostatic balance, which we will look at again. And we will look at the geostrophic balance in the horizontal, which is one of the most important large-scale balances, both in the atmosphere and in the ocean. Okay.